Did you ever wonder why high cholesterol levels increase the risk of a heart attack? Or maybe something simpler, like what makes soap actually clean? These aren't just random questions, they connect directly to this incredible world of lipids, molecules that touch, well, nearly every aspect of our biology and daily lives. Today, we're diving deep into Chapter 26, Lipids, from David Klein's Organic Chemistry, 3rd edition. Our mission to pull out the most, surprising insights, make the complex stuff truly clear, and explore the fascinating, often kind of hidden roles these molecules play all around us.
Yeah, and what's truly remarkable about lipids, right, is how they're defined. Unlike most organic compounds we talk about, they aren't categorized by a specific chemical group like an alcohol or a ketone. It's based on a physical property,
Hmm.
their aversion to water, their solubility. They're the compounds you can extract from cells using nonpolar organic solvents,
Yeah.
basically stuff that doesn't mix with water. And this raises an important question for you. What does that fundamental property, their water-hating nature, tell us about their incredibly varied functions? I mean, everything from building cell walls to signaling in your brain.
That's a perfect way to frame it. Okay, and this deep dive will guide us through 6 major classes of these vital molecules. We'll start with waxes, triglycerides, and phospholipids. These are often called complex lipids because of how they behave chemically. Then we'll shift gears to simple lipids, steroids, prostaglandins, and terpenes. It's quite a journey.
It is. From nature's waterproof armor to powerful internal messengers, all built from these, well, fat-soluble foundations.
Okay, let's start by unpacking that foundational distinction then. Complex versus simple lipids. You said it's about how they react with water. Complex lipids readily undergo a process called hydrolysis, meaning they can be easily broken apart by water, often because they contain ester linkages usually that are vulnerable to water.
Right. While simple lipids, on the other hand, don't break down easily in water, they resist hydrolysis. But it's important to remember, simple and complex here refer only to that behavior with water. It doesn't necessarily mean their structures are simple or complex.
Ah, okay. Got it.
Yet some simple lipids have incredibly intricate structures and vice versa. So for a quick preview, for complex lipids, think spermaceti wax or a triglyceride like, the fat in bacon, or lecithin, which you find in egg yolks. And for the simple ones, we'll get into cholesterol, a molecule like PGF2, which is involved in pain response, and limon that gives lemons their smell.
Fascinating. Okay, so let's begin with those complex lipids, starting with waxes. When you hear wax, you should probably picture nature's ultimate protective barriers. Chemically, they're typically made when a long-chain fatty acid links up with an equally long-chain alcohol. It forms an ester. Take triacontyl hexadecanurate from beeswax. It's essentially a very long, very stable grease molecule.
And the secret to waxes being such effective barriers, it lies in their physical properties. Those incredibly long, straight hydrocarbon chains. They pack together so tightly, it creates really strong intermolecular forces, London dispersion forces mainly. This makes them solid, stable even when it's warm, with surprisingly high melting points. It's this tightly packed, water-defying structure that makes them just perfect for their role as natural armor and protective coatings.
And nature's uses are ingenious. Sperm whales, for instance, they're thought to use spermaceti wax in their heads, maybe as a form of sonar.
Possibly, yeah. It's quite amazing.
And insects have waxy coatings on their exoskeletons, like a waterproof shell. Bird feathers repelling water, that's wax. Mammal fur, too, like lanolin on sheep. And plants use waxes like carnauba wax on their leaves to stop water loss. It's everywhere.
Absolutely. Protective coatings are a major theme.
Okay, so from external defenses, let's turn inward to the molecules that power our lives. Triglycerides. These are the main components of the fats and oils we eat, and they're the primary way our bodies store energy long term. Structurally, it's a glycerol molecule linked up with 3 long-chain fatty acids, triesters. And here's where it gets really impactful for our bodies. Triglycerides are incredibly efficient energy storage. They pack in over twice the energy per gram compared to carbohydrates and proteins.
That's right. We're talking, what, 9 kilocalories per gram for triglycerides versus just 4 kilocalories per gram for carbs and proteins. It's a remarkably compact way to store fuel. And the specific properties of any given fat or oil, they depend entirely on the fatty acids attached. These are usually unbranched carbon chains, typically 12 to 20 carbons long, almost always an even number because of how they're synthesized biologically. But the critical difference is whether they are saturated, meaning no double bonds, just straight linear chains, or unsaturated, meaning they contain one or more double bonds.
Okay.
And the profound impact of these double bonds, especially cis double bonds, is they introduce a distinct kink, a bend into the chain.
Hmm.
This bend drastically affects their shape and, critically, their melting points. Compare linear stearic acid with kinked oleic acid. Big difference.
That kink really makes all the difference. Okay, so predicting melting points. It sounds like there are clear trends. For fats with straight saturated chains, the melting point goes up as the chain gets longer. More carbons, higher melting point. Like myristic acid melts higher than lauric acid.
Makes sense. More surface area for those intermolecular forces.
But then you introduce a cis double bond, that kink, and it significantly drops the melting point. Those bent molecules just can't pack together efficiently in a solid. It's why oleic acid with one kink melts much lower than straight stearic acid, even though both are C18.
Exactly. And add more kinks, more double bonds. The melting point drops even further. They become more fluid.
Right. Which leads us to fats versus oils.
Precisely. This connects directly to how we classify triglycerides in everyday terms. Fats are generally solid at room temperature, like butter or lard. They're predominantly made of saturated fatty acids. Think tristerin. Oils, on the other hand, are liquid at room temperature, like olive oil or canola oil. They're predominantly unsaturated, full of those kinks. Think trialine. So this raises an important question for you. Thinking about your own kitchen, why do some cooking oils solidify in the fridge while others stay perfectly liquid?
Ah, it's those kinks again. The ones with more kinks, the unsaturated ones, stay liquid even when cold.
You got it. So when comparing triglycerides, remember two key features. Length of the fatty acid chains longer means higher melting point generally.
Yeah.
And the absence or presence of those double bond kinks mean lower melting points. That's the core idea from the skill builder focus in the text.
Okay, great. So what happens when we, chemically react with these triglycerides? They're so central to diet and biology. Let's explore some key transformations. First, hydrogenation. This is adding hydrogen across the double bonds in those unsaturated fatty acids. Usually needs a catalyst, like nickel. It saturates the chains, makes them straighter. It's a common industrial process, right? Like turning liquid vegetable oils into semi-solid margarine.
Exactly. But here's where it gets tricky. During partial hydrogenation, some of those double bonds can flip geometry, from cis to trans.
Oh, those fats.
Yes, trans fats. And it turns out these trans fats, created often to improve texture or shelf life, are strongly linked to raising LDL, the bad cholesterol, and significantly increasing the risk of heart attacks. It became a major public health issue.
Which is why the FDA mandated phasing them out.
Correct. A chemical tweak with really serious biological consequences.
Okay, another reaction, autooxidation. This explains why some fats go rancid, right? Unsaturated fats seem particularly vulnerable. Oxygen from the air attacks them.
Yeah, specifically at positions near the double bonds, called allylic positions. It kicks off a radical chain reaction, forming hydroperoxides. These break down further into aldehydes and ketones, which are responsible for that nasty, rancid smell and taste, and they can be toxic.
So that's why food manufacturers add antioxidants.
Precisely. Radical inhibitors, antioxidants like BHT or BHA, are added to intercept those radicals and stop the chain reaction, extending shelf life.
Okay, now for a really old reaction, hydrolysis. Specifically saponification. You treat triglycerides with a strong base, like sodium hydroxide or lye, and they break down into glycerol and the salts of the fatty acids, which are soap.
Literally soap. It's how soap has been made for millennia. It's a classic nucleophilic acyl substitution, if you remember mechanism 26.1 from the chapter.
So this raises that question you mentioned. How do these simple soap molecules actually clean?
It's all about their dual nature. They have a long, non-polar, water-hating tail, the hydrocarbon chain, and a polar, water-loving head, the carboxylate group. In water, they form these cool structures called micelles. The tails point inward, trapping grease and dirt, which are also nonpolar.
Like a little cage for grease?
Kind of, yeah.
Yeah.
And the polar heads face outward, interacting with the water, so the whole micelle, grease and all, gets washed away.
Brilliant.
It is pretty neat. Though traditional soaps can react with calcium and magnesium ions in hard water to form insoluble soap scum.
Ugh.
Yeah. Which is why modern synthetic detergents like sodium lauryl sulfate in shampoo were developed. They have a similar structure but don't form that scum.
And the skill builder here is about drawing the products correctly, right? Glycerol and the 3 separate soap molecules.
Exactly. Identify all 3 ester groups and show them breaking apart. And remember, animal fats tend to have more saturated fatty acids than most vegetable oils, leading to slightly different soap properties. Got it. And one more reaction. Transesterification,
Yeah.
making biodiesel.
Yeah. You can react triglycerides like used cooking oil, potentially with a simple alcohol like methanol, using an acid or base catalyst. The methanol essentially swaps places with the glycerol backbone. You end up with fatty acid methyl esters or phanes. These are much less viscous than the original oil.
And that's biodiesel, fuel from fat.
That's biodiesel. It can be used in diesel engines, a potential renewable energy source. The mechanism, especially the acid-catalyzed one, mechanism 26.2 in Klein, is interesting. It involves protonating the carbonyl, making it more susceptible to attack by the methanol, then a series of proton transfers, and finally kicking out glycerol. A key problem-solving point from Klein here. In acidic conditions, your mechanism should always avoid forming or using strong bases. Everything stays relatively stable.
Okay, fascinating stuff on complex lipids. Now let's shift to the simple lipids. Where do we start?
Let's start with phospholipids. These are absolutely foundational. They form cell membranes.
Right, they're kind of like triglycerides, but instead of a third fatty acid, there's a phosphate group involved, an ester of phosphoric acid.
Exactly. Specifically, we often talk about phosphoglycerides. Key types include phosphatidic acids, cephalins, and lecithins. You find lecithins in egg yolks, for example.
And their structure is key to their function.
Absolutely key. What's fascinating here is how their structure, typically two nonpolar water-hating tails and one very polar water-loving head group containing the phosphate, enables them to spontaneously self-assemble in water. They form lipid bilayers, two layers of molecules with the tails pointing inwards away from water and the heads pointing outwards, interacting with water inside and outside the cell.
And these bilayers are the cell membrane.
They're the main fabric, yes. They act as selective barriers, controlling what gets in and out, maintaining those vital concentration gradients essential for life.
Why are they so much better suited for this than, say, just free fatty acids or triglycerides?
It's their geometry. Fatty acids tend to form micelles, those spherical things like soap. Triglycerides just clump together as oil droplets. Phospholipids have just the right shape, sort of cylindrical or slightly conical, to naturally form stable, flat sheets, the bilayers.
Makes sense. And you mentioned a medical connection with antifungals.
Right. Medically speaking, it's a clever strategy. Fungal cell membranes use a molecule called ergosterol as a stiffening agent within their bilayer. Human cells use cholesterol. It's a subtle difference, but some antifungal drugs, like amphotericin B, specifically target ergosterol, they essentially bind to it and create pores or holes in the fungal membrane, killing the fungus while having less effect on human cells. It exploits that difference in lipid composition.
Very clever chemistry. Okay, next, simple lipid. Steroids. These are big players, right? Often hormones.
Huge players. They're defined by that characteristic tetracyclic ring system. 3 6-membered rings and 1 5-membered ring, all fused together, usually labeled A, B, C, D.
And that structure makes them pretty rigid.
Very rigid, yes. The rings are mostly fused in a trans arrangement, which leads to a relatively flat, stiff structure. This rigidity is important for their function. Like cholesterol, which acts as that membrane stiffening agent we just mentioned, it slots into the bilayer and modulates its fluidity.
Cholesterol itself. It looks complicated, lots of rings, methyl groups sticking off.
It is intricate. Note the 2 axial methyl groups and the side chain, which is usually shown equatorial. It has 8 chiral centers.
8!
But remarkably, only one specific stereoisomer exists naturally. Nature's synthesis is incredibly precise.
How does nature make something like that?
The biosynthesis is complex. It starts from a simpler terpene precursor called squalene. There's an amazing enzymatic epoxidation, then an intramolecular cyclization cascade, followed by rearrangements. It's beautiful organic chemistry orchestrated by enzymes. This raises that important question again. How does nature achieve such precise control over chirality, over the 3D shape in these multi-step processes? Enzymes. Their active sites act like tiny molecular molds and assembly lines.
Okay, back to cholesterol and health. We hear about good and bad cholesterol. What's actually going on there?
Yeah, that's really about how cholesterol is transported in the blood, because lipids don't dissolve well in watery blood plasma. They get packaged into lipoprotein particles. LDLs, low-density lipoproteins, are often called bad cholesterol. They transport cholesterol to the cells. If there's too much LDL, cholesterol can get deposited in artery walls, forming plaques atherosclerosis. That increases the risk of heart attack or stroke.
And HDLs?
HDLs, high-density lipoproteins, are the good cholesterol. They do the opposite. They pick up excess cholesterol from tissues and transport it back to the liver for processing or removal.
So a high LDL-HDL ratio is the risky part.
Exactly. That's a key indicator for cardiovascular risk.
Which brings us to statins. Drugs like Lipitor atorvastatin, or the original one, lovastatin. How do they help?
Statins are cholesterol-lowering drugs. They work by inhibiting a key enzyme, HMG-CoA reductase, which is involved early in the body's own cholesterol biosynthesis pathway. By blocking production, they lower overall cholesterol levels, especially LDL.
And didn't the first statin come from nature?
It did. What's fascinating here is that lovastatin was first isolated from a fungus, Aspergillus terris. It shows how nature is often this incredible source of inspiration for medicines. That discovery really launched the whole class of statin drugs.
Amazing. Okay, beyond cholesterol, steroids are also crucial hormones,
Right.
sex hormones.
Yes, you have androgens, the male sex hormones like testosterone, estrogens, the primary female sex hormones like estradiol. These characteristically have an aromatic A ring. And progestins, like progesterone, involved in the menstrual cycle and pregnancy.
They control reproductive processes, secondary sex characteristics.
All of that, yes. And synthetic versions are widely used in birth control pills, manipulating these hormonal cycles.
And there are other steroid hormones, too.
The adrenocortical hormones, secreted by the adrenal glands. Cortisone and cortisol are examples. They have powerful anti-inflammatory effects, so they're used medically to treat conditions like psoriasis, rheumatoid arthritis, asthma.
But there's also a downside with steroids, anabolic steroids.
Yes. Anabolic steroids are synthetic derivatives of testosterone designed to maximize its muscle-building anabolic effects. They have a history of abuse by athletes trying to gain an edge.
Do they actually work? And what are the risks?
The performance benefits are often debated and might be small, but the health risks are significant and very real. We're talking increased risk of heart disease, stroke, liver damage, even liver cancer, infertility, and serious mood disturbances, steroid rage.
So the risks seem to heavily outweigh uncertain benefits.
In almost all cases, yes. It raises important questions about personal choices, fair competition, and public health when these substances are misused.
Definitely. Okay, moving on from steroids, prostaglandins. These sound important, but maybe less familiar.
They are incredibly important, but they act differently. They're extremely powerful biochemical regulators, first found in seminal fluid, but now we know they're made in almost all tissues. Unlike hormones that travel through the blood, prostaglandins are local mediators, or local hormones. They act right where they're synthesized, influencing nearby cells.
And what do they do?
A huge range of things. They regulate blood pressure, blood clotting, uterine contractions, kidney function, nerve impulses, immune responses, inflammation, pain, fever. Really widespread effects.
Just structurally, what are they like?
They're derived from a 20-carbon fatty acid, usually arachidonic acid. The defining feature is a 5-membered ring within that 20-carbon structure, plus 2 side chains. There's a naming system, PG, for prostaglandin, then a letter, like E, F, A, for the ring substitutions, and a subscript, like 1, 2, 3, for the number of double bonds in the side chains. PGF2 is a common example.
And how are they made?
They're synthesized from arachidonic acid by enzymes called cyclooxygenases, often abbreviated as COX enzymes. It involves a complex radical mechanism, actually.
COX enzymes. That rings a bell. NSAIDs.
Exactly. This brings us to NSAIDs, non-steroidal anti-inflammatory drugs. Think aspirin, ibuprofen, Advil, Motrin, naproxen, Alev. Their primary mechanism of action is inhibiting those COX enzymes, thereby blocking prostaglandin synthesis. Since prostaglandins mediate inflammation, pain, and fever, blocking their production reduces those symptoms.
How is that different from anti-inflammatory steroids like cortisol?
Steroids work further upstream. They suppress the release of arachidonic acid itself, so they block the production of all downstream products, including prostaglandins and other related molecules. NSAIDs are more targeted at the COX step. Now, this raises an important question. Why is it crucial to distinguish between different types of COX enzymes?
There's more than one.
Yes, primarily COX1 and COX2. COX1 is sort of the housekeeping enzyme. It's present in most tissues and makes prostaglandins needed for normal functions, like protecting the stomach lining and regulating blood platelet aggregation. COX2, however, is mainly induced at sites of inflammation. It produces the prostaglandins primarily responsible for inflammation and pain.
So traditional NSAIDs like ibuprofen inhibit both COX1 and COX2.
Correct. Which is why they can sometimes cause side effects like stomach irritation or ulcers. They're blocking the protective prostaglandins made by COX1.
That led to the development of selective COX2 inhibitors, right? Like Vioxx and Bextra.
Exactly. The idea was to target inflammation, COX-2, without hitting stomach protection, COX-1. But, well, what's fascinating here is the delicate balance. It turned out that selectively inhibiting COX-2 while sparing COX-1 seemed to shift the balance of other related signaling molecules in a way that increased the risk of heart attacks and strokes in some patients.
So those drugs were withdrawn.
Many were, yes. It highlights how complex these biological systems are. Inhibiting one pathway can have unexpected, sometimes dangerous ripple effects.
And prostaglandins are a part of a larger family?
Yes, the eicosanoids. This broader class, all derived from 20-carbon fatty acids like arachidonic acid, also includes leukotrienes, thromboxanes, and prostacyclins. They often have reloaded but sometimes opposing biological functions like thromboxanes promote clotting while prostacyclins inhibit it. The body relies on a precise balance between them.
Wow. Okay, one last class of simple lipids. Terpenes. These sound more fragrant.
Often, yes. Terpenes are a huge and diverse class, very common in plants. They're responsible for many of the characteristic scents and flavors we associate with plants. Think pine, mint, citrus, lavender.
They're found in essential oils.
They're the major components of essential oils. And structurally, they follow a fascinating pattern called the isoprene rule.
Isoprene rule.
Yeah, it's an observation that, on paper, all terpenes can be conceptually broken down into repeating 5 carbon units that have the same carbon skeleton as the molecule isoprene.
So isoprene is the building block.
Conceptually, yes. An isoprene unit is basically a 5-carbon structure, a 4-carbon chain with a 1-carbon branch. Terpenes are built by linking these units together, often in a head-to-tail fashion during biosynthesis. Examples include morcine from bay plants, or ipine, the main component of turpentine from pine trees. Both are 10-carbon monoterpenes, made from 2 isoprene units.
And they're classified by size.
By the number of carbons, yeah, which is always a multiple of 5. Monoterpenes have 10 carbons, 2 isoprene units. Sesquiterpenes have 15, 3 units. Diterpenes have 20, 4 units. Triterpenes have 30, 6 units. And tetrapenes have 48 units, like beta-carotene, the pigment in carrots, or lycopene in tomatoes.
And they can have functional groups, too, not just hydrocarbons.
Oh, absolutely. Many terpenes are functionalized with oxygen alcohols, ketones, aldehydes. Think of menthol from mint, camphor from camphor trees, carvone, which gives spearmint its smell. The variety is immense.
Klein has a skill builder focus on spotting these units, right?
He does. The strategy is, first, count the total carbons, make sure it's a multiple of 5. Then look for the characteristic branching pattern, usually isopropyl groups or related structures. Then try to mentally divide the molecule into those 5-carbon isoprene skeletons. It sometimes takes a bit of trial and error.
Now, you said isoprene is the conceptual building block. What's the actual biological one?
Good point. The actual biochemical building blocks aren't isoprene itself, but 2 activated forms, dimethylallyl pyrophosphate, DMAP, and isopentyl pyrophosphate, IPP.
Pyrophosphate?
Yeah, that diphosphate group, OPP, is an excellent biological leaving group. Nature uses it to make the carbon units reactive for linking together.
So how does the biosynthesis work?
Well, what's fascinating here is that it's remarkably efficient. The biosynthesis of most terpenes involves repetition of just 3 core reaction steps. 1, loss of the pyrophosphate leaving group to form a carbocation. 2, nucleophilic attack, often by a pi bond from another isoprene unit onto that carbocation. 3, proton transfer, usually to quench a carbocation or set up the next step.
So nature builds complexity through repetition.
Exactly. DMAPP and IPP combine to make gerenyl pyrophosphate, GPP, the 10-carbon precursor for monoterpenes. Add another IPP, you get farnesylpyrophosphate, FPP, the 15-carbon precursor for sesquiterpenes. FPP is also a branch point.
How so?
FPP can dimerize 2 molecules joining head-to-head to form squalene, that 30-carbon triterpene we mentioned earlier.
The precursor to cholesterol.
Precursor to all steroids. So if we connect this to the bigger picture, it's incredible. A few simple building blocks activated with pyrophosphate and a handful of repeated reaction steps allow nature to construct this vast array of molecules. From the scent of a lemon, a monoterpene, all the way to human sex hormones, steroids derived from squalene.
Wow. Okay, we have really journeyed through the incredible world of lipids today, from that fundamental definition based on solubility all the way to their diverse and absolutely critical roles in, well, everything. Cell membranes, energy storage, hormones, inflammation, even the sense of nature.
It really shows the versatility of organic chemistry in biological systems. Different structures, different functions, all stemming from that shared property of being nonpolar or having significant nonpolar regions.
It's amazing.
Indeed. And this raises maybe a final important question for you, the listener. Given the profound impact of these molecules on your health, your food, the world around you. What other unexpected chemical connections will you start to notice in your own life as you continue to explore?
That's a great thought. Next time you hear about cholesterol or use soap or maybe just enjoy the scent of pine or citrus, you'll know there's this deep, rich layer of organic chemistry at play, shaping the world in countless ways. We really hope you found this deep dive both informative and inspiring. Thank you so much for being part of our last minute lecture family. We look forward to our next deep dive with you.